Hi, everyone. My name is Terrence Neumann, and I'm excited to talk to you today about justice and misinformation detection systems, an analysis of algorithms, stakeholders, and potential harms. I worked on this paper with Maria De-Arteaga from University of Texas and Sina Fazelpour from Northeastern University. Misinformation has unfortunately become ubiquitous in our day-to-day life. The surge in the spread of misinformation on social networks has raised deep concerns regarding the well-being of individuals, groups, and democratic societies. Misinformation has the potential to cause real harms to people by propagating false beliefs in critical moments, such as elections, public health emergencies, and humanitarian crises. Faced with the scale of the challenge, many platforms have turned to algorithms to automate content moderation decisions, and fact-checking organizations are increasingly adopting algorithmic tools for support. For instance, Facebook reportedly labeled 180 million messages as potentially misleading during the 2020 election season, while Twitter says that it labeled 300,000 during the same period. However, there is a lack of attention to the ethical risks that algorithmic biases, similar to those found in systems used to assist with hiring, policing, and medical diagnostic decisions, may present in automated misinformation detection systems as well. A brief outline of the presentation. I'll start by discussing the motivation for the informational justice framework, including its origins in the field of information science and the relevant extensions needed to study misinformation detection. I'll then apply this framework to study questions of justice resulting from decisions made by an automated misinformation detection system, and demonstrate how the framework serves as a useful tool by considering the interests of a broad set of stakeholders in misinformation detection. In previously studied problems of algorithmic fairness, a single stakeholder is directly affected by the choice of a decision maker. This makes understanding the players involved quite easy. For instance, in Obermeyer et al., the authors show how doctors' reliance on a tool to predict health risk was systematically biased against Black patients, such that at the same level of predicted risk, Black patients were significantly sicker. We can see that this leads to a distributional injustice in healthcare resources for underrepresented, or in this case, Black patients. But how do we extend these notions of justice towards an information environment? How do we grapple with different stakeholders and different notions of justice that might be relevant to them? Should we focus on the fairness of outcomes for the content creator, or the subject of the content, or the information consumer, for instance? Kay Mathiasen, an information ethicist, previously developed a working theory to answer questions of justice in the context of information and misinformation. However, we extend her theory to fully consider the stakeholders involved in misinformation detection. Consider stakeholders in relation to two informational items: a claim, like a tweet, newspaper, something similar, and evidence that either refutes or supports a claim. This could be textual evidence, or it could be survey-based. The source of information is the creator of the content. The subject of information is a stakeholder represented within the claim, either expressly or by self-identification with the true subject. The subject of information may not always be human, but when they are, issues of justice are pertinent. The seeker of information is someone actively searching for quality information on a given topic. Finally, sources of evidence are those individuals who generate evidence that either refutes or supports a claim. To provide a concrete example, let's analyze the stakeholders in a given claim. Pope Francis endorses Donald Trump for president. In this context, seekers of information will likely be either American voters or Catholics, as this is a claim regarding a candidate endorsement. The source of information was a fake news website that was then cited by several Twitter accounts. The subject of information is both Pope Francis and Donald Trump, and indirectly Catholics. One source of evidence, Snopes, a highly credible fact-checking group, found this claim to be false. Now that we understand the players, we can formulate different notions of justice that exist in this information environment. On this slide, we summarize proposed notions of justice relevant to the different stakeholders in the misinformation detection pipeline. While these notions are not necessarily comprehensive, they serve as an intuitive foundation for the conversations regarding informational justice. Mathiasen proposed three of these notions in her original work. First, seekers of information should have access to equal high quality information. If some group systematically receives lower quality of information from a biased misinformation detection system, then some seekers would face a distributive injustice in the quality of information they receive. If sources of information are unfairly moderated, having their content blocked at higher rates, then this forms a participatory injustice, rooted in notions of free speech. Next, if certain groups of subjects of information are the recipients of damaging misinformation at higher rates than others, this forms a recognitional injustice. Finally, if some sources of evidence regarding a claim are discriminated against in their knowing of something or systematically and unduly deemed less credible than others, this forms an epistemic injustice. With this framework established, we now apply it to study an abstract automated misinformation detection pipeline, pointing out potential systemic harms and suggesting possible sources of these harms. First, I'll provide a broad picture showing where we are going, and then I'll fill in the details for each subtask. This pipeline abstracts common tasks in automated fact-checking and was compiled in a recent literature review. It's worth noting that systems in practice may only implement one or two elements of this pipeline and keep human workers for the other segments. First, a checkworthiness algorithm scans a vast array of user content and determines which content is most worthy of fact-checking. Second, if a claim is prioritized for fact-checking, evidence is retrieved that either supports or refutes the claim. This evidence can either be a direct survey regarding the claim, or it can be passively gathered. Third, after a claim has been prioritized for fact-checking and evidence is retrieved, a predicted verdict can be generated. Let's focus now on the first stage in this pipeline, checkworthiness. These algorithms, as I previously mentioned, help prioritize scarce fact-checking resources for various claims made on social media. Large social media platforms, such as Meta, use checkworthiness to prioritize fact-checking. Several different methods have been proposed to predict checkworthiness of a claim. However, they all involve estimating a function dependent on the content of the claim and the metadata of a claim, such as likes, retweets, and the source of information. At this stage of the pipeline, we see that most, if not all, of the harms stem from false negatives, which is when something that is actually checkworthy isn't prioritized for fact-checking by the algorithm. In this case, subjects of information can face harm to their reputation if misinformation or rumor isn't ever fact-checked. And seekers of information interested in high-quality information will face a distributive injustice in the allocation of fact-checking resources. This is especially pertinent for high-stakes scenarios such as elections and humanitarian crises. Interestingly, it's not clear if false positives harm stakeholders, as long as false positives in this stage are uncorrelated to errors further down the pipeline. So where might these harmful false negatives come from in the checkworthiness pipeline? We claim that in the context of supervised checkworthiness algorithms, measurement bias and crowdsourced labels is likely part of the problem. For instance, there is evidence both in research and practice that people ask questions about the relevance of a claim to the, quote, general public as a measure of checkworthiness. This definition might bias the labels to systematically downweight checkworthiness of claims made by or about marginalized groups. In order to alleviate measurement bias in the labels, we see some guidance from the automated toxicity scoring literature, which states that using raters that self-identify with the subjects of comments can create more inclusive machine learning models and provide more nuanced ratings than those by random raters. Next, we'll examine evidence retrieval, the second stage of the pipeline. For claims deemed checkworthy in the previous step, evidence retrieval returns important metadata such as the relevance and stance of evidence in relation to the claim for each document in a corpus of potential evidence. Another approach for evidence retrieval seeks to actively crowdsource opinions or beliefs related to a claim. The major potential for harm in this task occurs when relevant sources of evidence are not considered credible or actively queried. For sources of evidence, this serves as an epistemic injustice as their knowing has been discredited. For seekers of information, if sources deemed credible by the algorithm do not engage with topics relevant to some groups, then no downstream verdict will be attainable for seekers, leading to a distributive injustice in the fact-checking resources. One highly relevant example of an epistemic injustice for sources of evidence has been documented by the New York Times in the context of image captioning. Many nuances of images of particular importance to Native Americans have been lost due to their extremely low representation in the data labeling workforce. For instance, in this image, we see a large group of Native American children sitting outside a boarding school. From the 17th through early 20th centuries, Native American children were separated from their families and sent to boarding schools where they were forced to assimilate to the new American culture and shed their own culture in this tragic process. In a data labeling experiment, Native American students labeled this image with tags such as genocide, tragedy, and cultural elimination. However, a leading image captioning algorithm had no nuance and labeled the picture crowd, audience, and smile. Where might these biases come from in an evidence retrieval system? In the context of a broader worldwide social media, there is a noted historical bias in the distribution of professional fact-checking institutions. These data come from the Duke Reporters Lab list of fact-checking organizations. On the rightmost column, you can see the fact-checking organizations per billion population across 6 continents. Interestingly, North America, Europe, and Australia are remarkably similar and have high levels of fact-checking resources. There are roughly 7 times more organizations per person in these continents than there are in Asia and Africa, potentially pointing to difficulties in gathering highly credible evidence for claims originating in Asia and Africa. Finally, let's examine the final and most consequential step in the pipeline, verdict generation. In this step, a verdict as to whether a claim is true or false or somewhere in between is predicted, and some action is taken to either label or remove a claim predicted to be misinformation. Because this is the step that triggers an action, the most potential harms are associated with this automated process. First, we see that false negatives, or predicting a claim to be true when it is in fact false, leads to harms for subjects and seekers of information for similar reasons that we saw in the check-worthiness stage of the pipeline. Subjects of information face a recognitional injustice if they are damaged by misinformation and the detection algorithm takes no action against the misinformation. Similarly, seekers of information face a distributive injustice of quality information, as misinformation will continue to spread as if it were true. Additionally, we see harms of false positives for sources of information. A false positive in this context is when a true claim is incorrectly labeled as false or misleading and is followed by some action being inappropriately taken on the claim. This can lead to a participatory injustice for sources of information, as their right to participate in the information ecosystem has been unjustly diminished. One potential source of these harms is measurement bias in the crowdsourced labels. Recent research by Allen et al. Found that if a crowd is not politically balanced, then labels will be biased in comparison to expert fact checkers. However, with a reasonably small politically balanced crowd, this bias disappears. A second potential source of these harms caused by the model may stem from aggregation bias in the crowdsourced label. For instance, imagine 20 people were surveyed regarding their judgments of a particular polarizing claim, which people either thought it to be certainly true or certainly false, and a simple average was taken to build the supposed ground truth label. This might result in a near neutral label when in fact there are likely 2 distinct distributions of opinions toward a claim. Recent research by Babet et al. Examines certain measures that can be used to provide more context to crowdsourced opinions regarding a claim, such as the ideological mean perception bias. I want to conclude by discussing some implications of this work. First, on the more theoretical side, our analysis didn't consider how these stakeholders really interact and which notions of justice are held higher by certain platforms. For instance, on Facebook, conservative sources of information claimed that they were scrutinized more closely than liberals. In response, Facebook changed their standard of detection only for conservative sources. However, this seems to imply that their claim to justice is more pertinent than that of conservative seekers of information who now face higher levels of misinformation in their newsfeed. Future theoretical work should examine these issues in more detail. Finally, more practically, we think that this analysis provides strong ground for algorithmic fairness audits of misinformation detection systems in relation to one or more stakeholders. In future work, we will be examining the fairness properties of check-worthiness estimation in relation to the subject of information. Thank you for listening.